And let's make a summary using this slide, because we talked about the several reactions that put the hydroxyl groups. I know I just talked about it. But let's just talk about it one more time, because these are definitely going to be a question in a meaningful way in the final exam. So you really want to know inside out. So starting with this double bonds, and then these are differently substitute double bonds. If you're doing just dumping in acidic water, strong acid like sulfuric acid in water, these are carbocation condition, right? Pi electrons against the proton, that makes the carbocation. The more substituted carbocation, right? That's basically for the molecular chemical products. Water capture that, but that molecule, if there's change to the rearrangement, it will happen. So that's something you're going to be worrying about the carbocation. But this one, it will not rearrange, so water capture that, and then you got the OH group there. That makes it up. You put just one OH. You keep the same thing. In other way, oxymercuration, demercuration is the base of the better way. Mercury acetate, little bit of water in there. It makes a mercury ion as intermediates. When you make a bridge ion, you see the mercury will pull the density from those two carbons. More substituted carbon, lose more density. And that's the one water makes an attack, right? And then it's a backside attack, so it's gotta be opposite side at the end of being. OH in the basically opposite side of the mercury. And then these methyl groups are pushed up. Why it gets pushed up? You gotta remember that, the inverted stereochemistry by the nucleophilic attack and sexual reaction, the same reason. When the water makes an attack, it pushes the methyl group to the other side. That's why methyl is the top here. And the mercury is still there, not gone, but it can be removed by the second step, which is the treating sodium borohydride. Then you get this. I mean, stereochemistry is not necessary. I'm just showing you because I just put it there, because these are symmetrical molecules, so it doesn't need to be, put the stereochemistry. Still makes a molecular product because the OH go to the more substituted side, which is the neutral parts here. There's another way of adding water, which is hydroboration. You are adding boron, BH3. It aligns to the molecule. Hydrogen and boron will be added on the same side, but the hydrogen on the more substituted carbon, boron on the less substituted carbon, and then the boron will be replaced by OH in the second step, which is an oxidative walk-up, hydrogen peroxide and sodium hydroxide. That will put an OH on the less substituted side, so we call this anti-Markov chemical products, right? Stereochemistry different at the same time, regional chemistry different. So this is something we discussed in last class. Now we just talked about another way. Oh, yeah, this is the first time we talked about because we talked about almost all of the expression alcohol double bonds. If you do bromination in water, right? These are halohydrin reactions. The bromine new ion will be formed first. It's a bridged ion. And then it's going to pull into density from those two carbon. Same thing. The more substituted carbon will lose more density. And that's the one nucleophile, which is the water here in the solution, makes an attack. And then again, it's a backside attack. It makes an attack from the opposite side where the bromine ion is. So you're going to end up having bromine and the hydroxy groups in the opposite position. It's going to be trans. And then the OH goes to the more substituted side, right? Because more electron deficiency are created in the more substituted side. So that's been the same thing so far. So that's the halohydrin reactions. That you make an alcohol with a halogen on the next carbon, you have to remember that because you cannot make this with any other reactions. After that, we discussed things we talked about today. You have epoxide formation, then opening epoxide in acidic conditions. So that makes epoxide being protonated, that pull the density from the carbon. Same thing, more substituted carbon, lose more. nucleophile water makes an attack on that carbon, backside attack. So you're going to end up having a 2OH on the opposite side, trans. Right? So a lot of the thing, basically repeat the same thing over and over again. It's just changing electrophile and nucleophile. So that's the basically what it is. So you get to make a trans diol. So that's the one, two hydroxy groups added in the vicinal carbons. You can, and then I would still consider this a monocritical product because the water is nucleophile, makes an attach to the more side, even though it's the same OH anyway, but I would still call it monocritical products. Another way is the osmium tetroxide, hydrogen peroxide, or manganate and the hydroxide, cold and dilute conditions. That's going to put the OH on the same side. It can be both top or both bottom, doesn't really matter, but both on the same side. So, you're going to have a different way to process double bond, creating molecule with the hydrogen groups, along with the many other things, along with the more than one hydrogen groups. And then sometimes there are different electrophile, different nucleophile used, and then you're going to produce different things. There are so many of things. And then if you're not knowing things in detail, you can easily get confused. I really want you to be careful, knowing all the details, and that's basically something we need to study.